The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
So there's two things we can do in space. And, you can look for the volume of solids, or you can look for the area of surfaces. So let me start with the easier of the two. Let me start with volumes of solids. And we'll go back to area, I promise. So I claim that there's also a notion of determinant in space, and that's going to tell us how to find volumes. So let's say that we have three vectors, A, B, and C. And then the definition of their determinant is going to be, so the notation for that in terms of the components is the same as over there. We put the components of A, the components of B, and the components of C inside vertical bars. Okay? And of course, I have to give a meaning to this. So this will be a number. And what is that number? Well, the definition I will take is that this is A1 times the determinant of what I get by looking in this lower right corner. So the 2 by 2 determinant, B2, B3, C2, C3. Then I will subtract A2 times the determinant of B1, B3, C1, C3. And then I will add A3 times the determinant B1, B2, C1, C2. And each of these guys means, again, you take B2 times C3 minus C2 times B3. And this times that minus this times that, and so on. So in fact, there's a total of 6 terms in here. Okay, and maybe some of you have already seen a different formula for 3 by 3 determinants where you directly have the 6 terms. It's the same. Okay, it's the same definition. So how to remember the structure of this formula? Well, this is called an expansion according to the first row. So we're going to take the entries in the first row, A1, A2, A3, and for each of them, we get a term. Namely, we multiply it by a 2 by 2 determinant that we get by deleting the first row and the column where we are. Okay, so here, the coefficient next to A1 is, well, we delete this column and this row, and we're left with B2, B3, C2, C3. Next, the next one, we take A2, we delete the row that's in it and the column that it's in, and we're left with B1, B3, C1, C3. And similarly with A3, we take what remains, that's B1, B2, C1, C2. Finally, last but not least, there's a minus sign here for the second guy. Okay? So, well, it looks like a weird formula. And I mean, it is a little bit weird, but it's a formula that you should learn because it's really, really useful for a lot of things. So I should say, if this looks very artificial to you and you'd like to know more, there's more in the notes. So read the notes. They will tell you a bit more about what this means, where it comes from, and so on. If you want to know a lot more, then someday you should take 1806, linear algebra, where you will learn a lot more about determinants in n-dimensional space with n vectors. And there's a generalization of this in arbitrary dimensions. In this class, we'll only deal with 2 or 3 dimensions. Yes? Sorry, why is the negative there? Well, that's a very good question. It has to be there so that this will actually equal, well, what I'm going to say right now is that this will give us the volume of the box with sides A, B, C. And the formula just doesn't work if you don't put the negative. there's a more fundamental reason which has to do with orientation of space and the fact that if you switch two coordinates in space, then basically you change what's called the handedness of the coordinates. If you look at your right hand and your left hand, they are not actually the same. They are mirror images. And if you swap two coordinate axes, that's what you get. That's the fundamental reason for the minus. But again, I mean, we don't need to think too much about that. All we need in this class is the formula. So why do we care about this formula? It's because of a theorem that says that geometrically, the determinant of the three vectors A, B, C is, again, plus or minus. This determinant could be positive or negative. See, there's minuses and there's all sorts of stuff. Plus or minus the volume of the parallelepiped that's just a fancy name for a box with parallelogram sides, in case you wonder, with sides A, B, and C. Okay, so you take your three vectors A, B, and C, and you form a box whose sides are all parallelograms. And then its volume is going to be the determinant. Okay. Other questions? Oh, at the back. I'm sorry, I can't quite hear you. Yes, we are going to see how to do it geometrically without a determinant, but then you'll see that you actually need a determinant to compute it, no matter what. So we are going to go back to this and see another formula for volume, but you'll see that really I'm cheating. I mean, the important way, I mean, somehow computationally, the only way to compute it is really to use a determinant. Yes? That's correct. In general, I mean, actually, I should say, if you look at the 2-by-2 determinant, see, you can also explain it in terms of this expansion. You take A1 and multiply by this 1-by-1 determinant B2. Then you take A2, you multiply it by this 1-by-1 determinant B1, but you put a minus sign. And in general, indeed, when you expand, you would start putting plus, minus, alternatingly. More about that in 1806. Yes? There's a way to do it based on other rows as well, but then you have to be very careful with the sign factors. So I'll refer you to the notes for that. Okay, if you did it with, I mean, you could also do it with a column, by the way. Just, I mean, be careful about the sign rules. So given how little we'll use determinants in this class, I mean, we'll use them in a way that's fundamental, but we won't compute much. So let's say this is going to be enough for us for now.